In this video, I'll explain how electronic devices store text, including their use of ASCII or Unicode, and delve into the specifics of string representation. Let's see how a computer stores a piece of text. Computers store information in a format of ones and zeros, so it is not possible to store the high string. So we need a way to convert a string into a binary format. And this is simple. Computers always do that. What we can do is to divide a string into individual characters and transform every one of them into a binary number. Now we have a simple characters mapping system, strings to numbers. So for the first letters of the English alphabet, A, B, and C, we could assign numbers 1, 2, and 3 for simplicity. Given this straightforward mapping that we just created and the letters A, B, C, D, E, F, we can build words and divide them by individual characters. For example, the word face can be divided by F with the number 6 assigned to it, A with the number 1, C with the number 3, and E with the number 5. So in total we will get 6135 for face and 312 for cap, and so on. And now it's not a problem for a computer to store these words because they are represented as numbers and can be converted into binary. This is what a real standard does, such as ASCII or American Standard Code for Information Interchange. It approaches the character mapping in the same way as we just did, with the one exception that numbers assigned to characters are different. ASCII assigns numbers from 1 to 128 and encodes one number into 8 bits or 1 byte. Thus, the letter A is assigned to the number 97, while the uppercase A has the number 65. The next letter after it, uppercase B, has the number 66, which is convenient. However, there are two major limitations to the ASCII encoding. The first one is that it can only encode 128 characters. The other one is that ASCII supports the English alphabet only, even though it supports common special characters such as whitespace, comma, dot, hyphen, and so on. So why support only 128 characters? Probably it's not a big deal to have more, right? ASCII was designed in 1961 and the first version of it was published in 1963. Back at that time, computers didn't have much physical storage. For example, in the 60s, computers had around 10 to 100 kilobytes of memory, while the average contemporary computer may have at least 100 gigabytes. If we calculate how much storage ASCII encoding took on the low-end 60s computer, we may see that it took around 1.3% of the total computer storage, which isn't too much, but it was still a substantial number. But as the computer storage space was increasing over decades, ASCII encoding took less and less space, so it made a lot of sense to extend ASCII encodings to overcome the limitations. This is when Unicode appeared in the 90s. So we don't call it the second ASCII version. It's a new and different standard. Even though it's a new standard and right now it's being used almost everywhere, the goal is still the same as it was for ASCII, with the difference to overcome the limitations of the predecessor. The mapping mechanism is still the same. It assigns numbers to characters, and those numbers are converted into binary. A difference here is that Unicode supports a much broader space of characters. For example, the letters A and B have the same number assigned as in ASCII, but there are characters that go way beyond these numbers, such as this character that is used in Chinese, Japanese, and Korean languages. The number assigned to it is 172,217. So the binary number for it is much longer and takes more bytes to store. We'll get back to the size soon. To represent small and especially large numbers more conveniently, Unicode also uses hexadecimal representation because it is shorter. Another representation uses a static string U plus and a hexadecimal string. Those are named Unicode code points. They are used as unique identifiers for characters. In a nutshell, a number or its binary representation or hexadecimal string or Unicode code point, they all represent the same thing but in different base system. The challenge is to decide how we encode a number into binary. For example, the number 97, which corresponds to the letter A, will take 8 bits or 1 byte in binary representation. And this is what ASCII does. It is the simplest encoding possible. But an interesting question arises when we want to store a number that is bigger than 8 bits. ASCII will store everything in 1 byte because it doesn't support larger numbers. For example, ASCII doesn't have this Chinese, Japanese, Korean character because it cannot store this huge number, since it will take 3 bytes minimum. But Unicode does support these characters, and this is where various encoding standards come into play. For instance, UTF-8 can store any Unicode character. So it stores the characters A and B in 1 byte, just like ASCII does. But it can also store the character with the number 172,217 in 3 bytes. UTF-8 is the variable length encoding, meaning that it can store a Unicode character in 1, 2, 3, or 4 bytes, so the size will vary. Characters in the ASCII range are represented by a single byte. Characters outside the ASCII range are represented using the sequence of bytes, where each byte starts with a prefix indicating the number of bytes used to encode the character. There is UTF-16, which is also a variable length encoding, but it can occupy either 2 or 4 bytes. And there is also UTF-32, which is different from the previous two because it is a fixed length encoding, meaning it stores everything in 4 bytes, which is 32 bits. Among all these encodings, UTF-8 is the most popular, but you may ask why there is a need for UTF-16 and UTF-32. The short answer is that the other two encodings are being used for specific purposes, usually to optimize string operations such as indexing and slicing. Let's review what we've learned. Strings must be converted into binary numbers, so we can store them in computers. ASCII was a popular encoding standard until we required the support of more languages. Nowadays, Unicode is the most widely adopted text encoding standard. Unicode uses various encoding standards such as UTF-8 to encode character numbers to binary. Thanks for watching. I hope you learned something new.